Let's do this. Yeah, so if you have the mini exam for me, I'll take that now. Thank you. Thank you. Name. Okay. All right. I had your next mini exam, I printed it and I left it on the copier. So I'll give it to you next time. All right, we're going to pick up where we left off. We had started talking about equations of lines and planes, right? And it said that the way we can create a line using vectors is this idea right here. It is right here. Okay, so the main idea is this. We all know that this is the equation of a line back from college algebra. What we're trying to do is draw the same line using vectors, right? That's the main difference. So the way we do it is we say, all right, we're going to start with some initial vector, r0. Okay, r0, that vector is going to take us to some place, some position in two-dimensional space or three-dimensional space, depending on whether or not this vector has 2 or 3 components. So even though the picture's on a flat sheet of paper, this applies to lines in 3D also, all right? So you have an initial vector that points you to some place on the line. And then what we need to do is we need to find another vector, which is parallel, this vector that is parallel to the line. And remember, that red vector could be over here, right? Vectors can move around. So it could be over here, yes? Or anywhere. But we want to make it attached to the tip of the vector r0. And if we do that, so if we add to this that vector v, then we will wind up being here at this point. And that's a new vector. This is r. So this thing right here is r. The vector r. Now I'm leaving some things out intentionally because we don't want just this point, we want all the points on the line. So what we want to do is we want to scale v, make it grow, shrink, flip over, other side, grow. So we want all scalar multiples of v. So we put a scalar in front of here. Now normally we've used c for scalar, or scalar, or like c, but here I'm going to use t instead. So t times v should be some vector that's parallel to t. And then now the vector where we wind up, this resultant vector, where we end up being on the line, is now a function of t. It depends on t. So we call it a function of t. And that is the master formula for the equation of a line in 2 or 3-dimensional space. Thank you. So we have this vector right here corresponds to some kind of initial point. Now this is not really correct for me to write initial point because that is a vector, not a point, right? But it points to a point. And so that's going to take us to our initial point. This right here is what we call the direction vector of the line. Okay? That's your direction vector. And of course, this is just some scalar that gives you all the multiples of v. Does this picture make sense? Does the formula make sense? Kinda? Audrey? Yeah. Okay. All right. Now, when I was taught this, I remember my professor. He did this a little different. He used a different formula. It was u plus tv. That was the formula I learned this way. And the thing that was it was the same thing, right? Instead of R naught, call it U. Instead of, well, everything else is the same, right? So just instead of R naught, call it U. And my professor, he made it easy to remember the formula because he called it the couch potato formula. Right? U plus a TV is a couch potato, right? It was easy to remember, but our book presents it this way, so I'm going to present it this way, all right? Now, let's see what we can do with this. Oh, by the way, I should have mentioned this. To get the vector v, to actually get it, what we did was we picked another vector, r1, and we took r1 and subtracted r naught, and that's how we get v. So we're going to go through an example. So this is everything I just said. Yep. Yeah, I'll take that. Stapled. It's got to be stapled. You can turn it in afterward if you don't have a stapler. I'll come back to the end of that note. I really want to do an example. Let's do a three-dimensional example. We're just going to do part A here. Okay, so I give you 2 points in three-dimensional space, right? 2 points define a line, as long as they're different points. And we want to find the vector equation of this line. So first thing to do is maybe write down the formula, right? R of t equals r naught plus tv. So in order to have the formula, we need to come up with two things. We need to figure out what r naught is, and we need to figure out what v is. If we have r naught and we have v, we're done. Okay, so first let's do r naught. I'll do it over here. For r naught just has to be a vector that corresponds to any point on the line. And we're given 2 points, right? So we can use either one. So I'm gonna write 3, 6, negative 4 as my r naught, but I'm gonna write it as a vector. 3, 6, negative 4. Boom. Okay, that's it. Now, to find v, which is the direction of the line, I'm going to create a vector that goes from here to here. So imagine you got 2 points, right? So you want to create a vector that goes from one point to the other. And actually in this one, it doesn't matter the order you do it, but I'm just going to go from this one to this one, all right? So how would I do that? Yep, I would go 7 minus 3, comma, 14 minus 6, right? And then negative 7 minus negative 4. And this will be my direction vector. 4, 8, what's that, negative 3? Everyone agree? Okay, that's it. I have the initial position vector, and then I have the vector that's parallel to my line. And so if I put it together over there, I'll have my vector equation of the line. So this is going to be the vector 3, 6, negative 4 plus t times the vector 4, 8, negative 3. And what I'd like to do now is put these together, all right? Because these are vectors, we can add them. All right, we can add them together. But I also have t as a scalar, isn't it? Yeah. So that t can go through to each of these. So I'm going to do that first. So I have 3, 6, negative 4 plus 4t, 8t, negative 3t. Right, that's just distribution of the t through. And then adding the vectors, you just add the components together. Right, if I have 2 vectors in three-dimensional space, to add them, I add the x components, y components, z components. So I will get 3 plus 4t, comma, 6 plus 8t, comma, negative 4 minus 3t. There it is. And I'm going to state here t is an element of the real numbers. T is an element of the real numbers. So if you would like to draw the line, Okay, if you'd like to draw the line that contains those 2 points in three-dimensional space, what you could do is use this vector equation and just start plugging in values of t. Right? What would I get if I plug in t as 0? You get 3, 6, negative 4, right? Which would have just put you right there, right? Now this is interesting. What would happen if I let t be 1? I get the second point, don't I? So it's like if you imagine having those 2 points, right, in three-dimensional space. And we have almost like, I guess you could say it's a clock. If we start the clock at 0, we're here at this first point, right? Now as we let t start to go from 0 to 1, we're going to start drawing the line towards the other point, right? And when we get to t equals 1, we'll be at the other point. And when we get to t equals 2, we'll be out here, and t equals 3, and then t equals 4, right? And then if we were to go the other way, if we could like rewind, go backwards, t negative, then we'd start drawing the opposite direction. Yeah? Questions on that? Okay. You can almost see the similarities between this. I mean, that's our equation of our line on a flat sheet of paper. There's no vectors involved here, right? No vectors at all. But there are some similarities between this and this. Right? The b here corresponds to a point on the line, right? And then the m is like the pitch of the line, and the x is like the clock that's running. Here, that's what we have. This is like the b. It's a point on the line. The v is like the slope, right? Because it's the direction vector. And then the t is kind of like the x. All right, let's rewind here a little bit, back to the notes. So when you have the vector equation of a line, I'm going to leave, yeah, I might be able to do it that way. Let me leave our answer up. Okay, here's our answer, right? So it looks like this, doesn't it? Isn't that what ours looks like? Yep. Okay. We have x naught, we have some number in front of t, and then y naught, and then we have some number in front of t, and then z naught, and then we have some number in front of t. These three components, if you look at them individually, would look like this, right? Here's your x component, this is your y component, this is your z component, right? These have special names. The x component, right, is 3 plus 4t. The y component for us would be 6 plus 8t. And then the z component would be negative 4 minus 3t. These three equations are known as the parametric equations of that line. So this is the vector equation of the line. Okay, if someone were to ask you, hey, give me the vector equation of the line through these 2 points, that's the answer. But if they ask you for the parametric equations of the line through those 2 points, these three equations are your lines. I'm sorry, not your lines. These three equations are your answer. All right? Notice that when you look at the parametric equations, they don't look like they have anything to do with vectors, right? But the vector equation of a line is very clear that it is a vector. And then there's one more thing that we can ask for. Vector equation, parametric equations. The other thing we can ask for are what are called the symmetric equations. So the symmetric equations look like this. And let me just show you how you come up with symmetric equations. Because it looks like it might be complicated, but it's really not. All you do is you notice that your three parametric equations all have t in them, don't they? So I could solve each of one of them for t. So if I solve this for t, I would get, let's see, x minus 3 over 4 equals t. Isn't that what I would get? Just move the 3 over, divide by 4. Yes? Okay. And then on this one, same thing. Solve for t, you get y, go ahead, minus 6 divided by 8. That's t. But then this one, if we solve for t, is z plus 4 over negative 3. Okay, we can leave it like that. That's fine. That's t, right? So this is t, but that's t, but that's t. So if they're all t, they're all equal to one another, aren't they? And what we can get is set them all equal to each other. So x minus 3 over 4 equals y minus 6 over 8 equals z plus 4 over negative 3. And this is called your symmetric equations. So when it comes to lines, using vectors now in two-dimensional space or three-dimensional space, we have three ways we can represent them. Vector equation, parametric equations, symmetric equations. And they all have their pros and cons, I guess. Like which one, you know, you're looking at, they all kind of, I don't know. Sometimes it's best to look at the symmetric equations. Sometimes it's best to look at these. Sometimes it's best to look at that. Also, I'll point something out here. Notice in the symmetric equations, do you notice what the denominator numbers are? They're what? They're numbers. They are numbers, yes, but there's something special. Those were the numbers that were in front of t. They're what? They're... no one said it yet.
They were originally the components of the...
They're the components of the direction vector. Remember the direction vector v?
Yeah.
Those are the components of v, and they will always be the components of v. The denominator here will always be the components of v. And you can kind of see it here. We call it, or I call it in the notes ABC. So if I scroll up, when I define v, here it is, v. Here's the direction vector. I define it as ABC. When you write your symmetric equations, the denominators will always correspond to those components. It's just good to know. Yes?
Just real quick, you said that we could choose or not to be any of the two sets of...
Yes.
Okay.
Yep. So you could have an answer that looks different than this.
Okay.
Okay? But I promise you, if you write it in the symmetric form, you're going to have this direction vector will be the same as the vector form. Yeah. The direction vector is not unique because you can take any 2 points on the line to create your direction vector. So if someone picks different points, your direction vectors will be different. The thing is, they'll all be parallel to one another. No matter what, your direction vectors should be parallel. And remember that parallel means scalar multiple, not like it can point the opposite direction and still be parallel. All right, let's see if we can finish up this problem. So we did part A, right? Part B, sorry?
We did example 2 and example 1.
Oh, I didn't go far enough, sorry. I meant to go there. Okay, so find the parametric equations. We did that, right? Find the symmetric equations of the line. Did that. How about part D? Find where this line intersects the YZ plane. Now that's different, right? That's different. So where does this line intersect the YZ plane? So think about that. What does that mean?
That means that z will be 0, or wait, x will be 0.
X has to be 0. So if you're on the YZ plane, remember the room, right? The room is our, let me turn the light back on. Remember the room is our X, Y, Z. We've got that going on here. So the YZ plane is that's x-axis, y-axis, right? Z-axis. The YZ plane is this wall, right? And we want to know where that line that was sitting in three-dimensional space hits this wall. Well, if you're on this wall, your x-coordinate has to be 0. Good. Does everyone agree with that? Your x has to be 0. So for part D, this means that x must be 0, right? If you're on the YZ plane. Now, how does that help us?
Plug it into your symmetric equations.
Go back to, you can go to your symmetric or your parametric, right? So let's look at the parametric first. My parametric, you have them for me. What was it? X was 4t plus 3?
Yeah.
Okay, and then y was
8t plus 6.
8t plus 6. So you flipped them over, right? Everyone's okay with that, right? I mean, we can do that. Z is
Negative 3t minus 1.
-1. Everyone agree those were our, oh, 4, sorry. Those were our, what do we call these? Parametric equations. So if I know that to hit the YZ plane, x has to be 0, then I can just take that first parametric equation, replace x with 0, right? And what will that let me solve for? T. And once I know what t is, I can go into these two and find y and z. So I'll have x is 0, and then I'll be able to find y and z. So let's let x be 0. Oh, now this is going to suck, I guess. So what's t? Negative 3/4. All right. So once we know t is negative 3/4, now we go and we try and find what y is.
I think it should be 6t plus 8. 6 plus 8t, never mind.
Okay, so yeah, that's all right. Yeah, I wrote them down the other way, but it's okay. All right, so now we are going to say, we're trying to solve for what in this equation? We're trying to solve for what?
T.
Not t, for y, right? We have t, we're trying to solve for y. So t is negative 3/4, so y will be equal to 8 times negative 3/4 plus 6, which means that, let's see, y is equal to 0, okay. That worked out nice. And then now, coming in here, z is equal to negative 3 times negative 3/4 again, right? And then minus 4. 9/4 minus 4, which is same as 16/4. So negative 7/4, yes. All right. So what's my answer?
0, 0, negative 7/4.
So our answer is a point, right? 0, 0, negative 7/4. Because we want to know where the line intersects this plane. It's going to intersect it at the point 0, 0, negative 7/4. So it's actually right there on the z-axis, isn't it? It's on the z. It just happens to be for this example, all right? Just worked out that way. Does that all make sense? We had two, I think that's pretty amazing. You have 2 points sitting in three-dimensional space, and from that, we were able to determine a line through it, and we can actually tell exactly where that line would hit this plane. And you could do it for the xy plane. You could do it, xy plane. You could do it for the xz plane, right? They all would just correspond to replacing either x with 0, y with 0, or z with 0. We good? Okay.
You said you could also deal with the symmetric equations or just the parametric?
The symmetric, I think, might be a little tougher because you have two equal signs between them, right? So if you replace, you have x in there, right? So you could replace it with 0, but you can only solve for one of them at a time. You know what I'm saying? Then you'd solve for y, figure out what it is, and then you would have to set up another equation and solve for z. But it would work. It would just be a different approach. I think that way is pretty clean, though, right? You just figure out what t is, and then once you have t, you get everything. On example 1, it had asked for a point in two-dimensional space for you to find another point on the line. So what if I added that to this? If I added like a part E and I said find another point on the line, what could you do?
Set t equal to one side random.
So you go back to your vector equation, right? R of t was equal to, and then we had those three components in here, whatever. We know what happens at 0, right? At 0, we're there. And we said at 1, we're here, right? So just pick any other value of t, and it'll give you another point on the line. So just plug in 3, plug in 10, plug in negative pi. It doesn't matter. You'll get another point, right? All right, so I want to make sure you're clear on that. Now, sometimes we don't want to draw the whole line. Okay, sometimes we don't want to draw the whole line, and all we want to do is draw a line segment from one point to the other. Now this note, I'm going to skip it because I think it just confuses things. Let's just go back to this one. All right? And what if I say this? Find vector equation which draws line segment from 3, 6, negative 4, 2, 7, 14, negative 7. So find me the vector equation that draws the line segment that you know, it's going to start somewhere and stop somewhere, right? So the only thing that we're going to do differently is restrict our domain on t. We're going to come up with the exact same vector equation. We still do our r naught, we still do our v, but we restrict t between what, do you think? 0 to 1, right? Because at 0 you'll be here, and at 1 you'll be here. Understand? Now, what if I switch this? So what if I wanted to go from 7, 14, negative 7 to 3, 6, negative 4? What if I want to go the other way around? So what would my r naught be here?
Doesn't matter.
Well, it's still going to draw the line segment, but in terms of if I want to start from here and end here. If I wanted to start at that point,
It has to be your R naught, right?
does not have to be my r naught. Your r naught can be any point on the plane.
Oh, I thought you said it.
Any point.
Oh, I thought, but now it. Okay, never mind.
Yeah, it can be any point. And it really doesn't matter what r naught is if you're drawing the whole line. But if you want to draw it, if you want to start, think about it like a clock, right? So if I want to start the clock and be here, and then, you know, run my time from 0 to 1 and end here, then my r naught has to be this one. Okay, where my starting point is. So I'm going to have t 14, negative 7. Okay, that'll be my r naught. Now what's my direction vector? From here to here, right? So it's the opposite or negative of the vector we did earlier, which will now be negative 4, negative 8, positive 3, right? So the vector equation should be r of t equals this plus t times this, right? This plus t times this. So 7, 14, negative 7 plus t times negative 4, negative 8, 3. And then t is between, nope, that's not right, 0 and 1. See, I'm not saying that t can be anything. If t was everything, right, all real numbers, we just draw the line again. But I want to make it very specific that t is going to start at 0, end at 1. And now you can see that if I plug in 0, what happens if I plug in 0 for t? 0 here kills that, right? And where are you? Here. And that's the first point. But then if t is 1, I'm going to have 1 through here. So it's going to be this vector plus this vector. When we add 7, take away 4, we'll be at 3. We have 14, we'll take away 8, we'll be at 6. And then we have negative 7, and add 3, we'll be at negative 4. So we'll end where we want to end. Any questions on this? All right. Determine that these lines are skew. That is, it's supposed to say they do not intersect, and they are not parallel or orthogonal. Okay? I want you to show me that these two lines don't ever hit each other, they're not parallel to one another, and they're not orthogonal to one another. So two lines sitting in space. Three-dimensional space?
Yeah.
Yes, because they have 3 components. So I have 2 lines sitting in 3-dimensional space. I want you to prove to me that they're not parallel to one another. I want you to prove to me they're not orthogonal to one another. I want you to prove to me that they never hit each other. All 3 of those things. If I can show all those things, then we say these lines are skew. Now, first thing to notice, I'm calling this L1, right? And I'm just writing out 3 components. And doesn't that look like what we had when we did R of t and put it all together? We had like a number plus t and then a number plus something in front of t and then a number plus something in front of t, right? And I'm using t here, right? But here I'm using s. So t and s are like dummy variables. We could use anything we want. The reason I'm using s and t, using different variables, is because, and this is kind of subtle but important, if I let t vary through all real numbers, I'm going to draw a line, right? But it's going to draw it like one point at a time. If t is 0, we're going to be somewhere, right? If t is 1, we're going to be somewhere else. Here, if I let s vary through all real numbers, I'm going to draw a different line, right? The points, it doesn't matter the order in which the points are drawn. So like if I guess what I'm getting at is if I use t for both of these, then you might think that somehow the t's are connected to one another. But they're not. The t's are completely irrelevant. All right? They're on different clocks, so to speak. And they draw a line. So let's try and get through this. Let's take the easier parts first. What would be the easier part, you think?
Proving that they're not parallel.
That they're not parallel? Okay, how would you prove to me that they're not parallel?
They're not scalar multiples.
They're not scalar multiples. Now, when you say they are not scalar multiples, what do you mean by they are not scalar multiples?
L1 is not a scalar multiple of L2. I said that.
Each vector.
You're on the right track.
Components.
The
The components like each have to be, like if you compare them to L2, each component has to be can be multiplied by the same factor to get to the L2 component.
I'm with you, kind of. Both of you, I think, are on the same page. Do you have something?
Yeah, you can extract the direction vectors from those equations and prove that they're not scalar multiples.
So all of our lines are made up of two pieces, right? R naught, TV, right? So the R naught is just where you are, and the t is just going to multiply your direction, and the v is the direction vector, right? That's the big important part. Gives you like the slope of the line. To say these two are parallel means we need to compare their direction vectors, right? Not this the way it is. We need to, I like the word, extract their direction vectors. So let me just think about this. This vector right here, or this line, right, has a direction vector v, and I'm going to call it VL1. I know that's a lot of subscripting, but that would be the direction vector of L1, wouldn't it? And what is the direction vector of L1? How are you going to get it?
Take out R naught by
Okay, so R naught is where here? In this,
the 1 minus
the 1, the minus 2, and the 4, that's R naught. And then everything with a t in it was what we got after we distributed the t through the direction vector, right? So shouldn't the coefficients on the t be our direction vector? Like there's a 1 here, and there's a 3 here, and there's a 1 there, a negative 1 there, right? So the direction vector of L1 is the vector 1, 3, negative 1. We all on board with that? What's the direction vector of L2? Hold on, don't tell me. Cameron's going to tell me. Where's Cameron? Cameron is not going to tell me. Travis is going to tell me.
Should be
2,
1.
1,
Wait, shouldn't it be 0?
hold on, where?
No, never mind.
You said 2, 1, 4. 2, 1, 4. Good. 2, 1, 4. So we're looking at these direction vectors, and I mean, that's the pitch of the line, right? So if they're parallel lines, these vectors have to be scalar multiples of one another. Yes or no? Is there a way to turn this vector into this vector by just multiplying it by a number? No. Because the only way you can make 1 turn into a 2 is to what? Double it, right? But then if you double 3, you need 6 here, right? These are not scalar multiples of one another. So I can write it this way. VL1, right, is not a scalar multiple of VL2. Does that make sense? That vector is not a scalar multiple of that vector, and therefore, 3 dots means therefore, all right? This means therefore. Therefore, L1 is not parallel to L2.
Can you say one more time how you determine they're not scalar multiple?
Okay, so scalar multiple means I would have to be able to multiply this vector by a number all the way through and create that vector. So the only way to make that 1 turn into a 2 would be to double it. So imagine I put a 2 out here and double everything. Then I'm going to get 2, 6, negative 2, and that won't match up.
Could
And
you
it-
do it backwards too? Like
Yeah, the other way around. Like, how could I make the 2 a 1? Half it, right? But if I half that, I'm not that, right? As soon as one of them fails, you're done. Okay, good. Next thing, they're not parallel. You want to see if they're perpendicular? See if they're orthogonal? How would you do that? Dot product. Dot product the two direction vectors. If these dot product to be 0, they're orthogonal, right? So this was the check for parallel. Now for the orthogonal, we're going to take the direction vector L1 and dot it with the direction vector L2. And let's see what we get here. Now dot product, remember dot product is the easier of the two to compute. Cross product is a little bit more involved. So when we dot these, let's see what we get. Hold on. Chad? Where's Chad? No Chad? Oh, okay. Dot product on that. Go ahead and just read out each of the.
Could be
So the dot one is just first components multiplied, right?
So, yeah, it'd be
2 plus,
plus
because their answer is a number. 2 plus 3 minus 4, and that is 1, and that is not 0, and therefore they are not orthogonal. Therefore, L1 and L2 not orthogonal. All right, so far so good, right? We have to show all these things to show skew. Now the hardest part. How are we going to show that these lines never hit one another? What do you got?
Find the parametric equations.
Okay.
Choose some arbitrary value for an arbitrary variable, really, so x.
Mhm.
Choose some arbitrary value for x. Find what t and s, find what t of L1 has to be for x to equal that number. Find what s has to be for L2 to equal that, for the x component to equal that number.
Okay, I think I know what you're doing. Let me ask you something though. What value do you want me to pick for x though?
Any arbitrary one, really.
Okay, so let's say I pick 5.
Yeah.
What guarantee do I have that either of these lines ever hit 5? I'm with you. I understand what you're trying to do, but I see kind of that might present a problem. Because what you're saying is,
I see what you're saying. I did think about that, although now that you mention it, I can see that they should hit every x, y, and z value since none of those since none of the components of the direction vectors are 0.
okay, so you're looking at the fact specifically for this problem, the fact that, okay, so maybe I could give you a problem that did do that.
Yeah.
Then how would you attack? You know what I'm saying?
Yeah.
So let's go with something that's more general that's going to work every time.
Okay.
Okay? So think about this. If these hit each other, right? If these hit each other, so if they intersect, then there must exist a T and S such that L1 and L2 are the same. at those, at those values of t and s. I know this sounds weird, but let me just try and explain it. All right. If these hit each other, right? If these hit each other, then there is some x-coordinate, y-coordinate, and z-coordinate that these will have in common, right? So maybe, like, let's just say it's 2, all right, or 5. If there's a 5, let's say that this is going to be 5 and this is going to be 5, then there's some t that would make this 5 and some s that would make that 5, right? So these would have to be equal to one another at the same time. So there's a t and an s that make these the same. But simultaneously, the same t and the same s must make the y components equal and the z components equal. So that's what I'm saying here. If they intersect, there has to be some t and some s such that these two lines, every part of them, all three components, are identical or are the same at those values of t and s. So I have this.
Do you add up like the components of each vector and then like set them equal to each other?
I'm going to set them equal to each other. I'm not sure what you mean by add them up.
Like, so then you're not going to set like the x's or like the I hats equal to each other. You're going to set all of L1 equal to all of L2.
Yes, I am going to set all of L1 equal to all of L2, but that actually is the exact same thing as setting each of the components equal to one another.
Oh.
So it's one and the same. So I need this. So we need to find t and s where that will be true, right? I'm going to call this number 1. We need number 1 to be true, right? We also need number 2 to be true. Negative 2 plus 3t must equal 3 plus s. And we need 1/3 last condition, and that's for the z components to match. 4 minus t must equal negative 3 plus 4s. And what we have here is a system of linear equations. We have 2 unknowns and 3 equations, right? 2 unknowns and 3 equations. So I'm going to just make this look a little bit different for us. S, 2s minus t equals 1. Let's see here. S minus 3t equals negative 5. And then last one, 4s plus t must equal 7. I think I did that right. Basically what I'm doing is I'm moving all my s's and t's to the left, or getting them on one side and all my constants to the other. So this is what I should get when I do that. And now it's a little easier to see you have a system of equations. 2 unknowns, 3 equations. So how do we solve a system like this? You have more equations than unknowns. If you had it the other way around, we wouldn't be able to get a solution. If you have more unknowns than equations, we're not going to have a unique solution. If we have more equations than unknowns, then there could be a solution. So how can we go about this? Solve 2 of them, right? Just solve 2 of them first. Just ignore this one for now and treat this like a 2x2. Which one do you want? Oh yeah, okay, you want to do that one? Yeah, let's do that one. So let's solve that system right there. How would you solve this system? You have 2 options. You have elimination or substitution. I think elimination works great here because we'll just add down, right? So 6s, t's are gone, equals 8. So we get from there 6s equals 8, and that means that s is 4/3. Okay? So in order to make these 2 equations equal, right, to satisfy both of them at the same time, we need s to be 4/3. So how are you going to get t? Substitute. Now take this answer, let's plug it into either this one or this one. First one? Okay, so I'll do in the first one. So going in here, I get 2 times 4/3 minus t equals 1. And let's solve that there. 8/3, bring the t over, subtract 5/3?
Yeah.
5/3. So this should be t is 5/3. I'm going to trust that you could solve that equation. All right, so far, to make those two equations simultaneously true, we need s to be 4/3 and t to be 5/3. So is that it? Are we done?
You have to check it for the other.
Now we need to make sure that s and t plugged into that equation still give us -5. Right? So does it work? If I plug 4/3 in right here, and I plug in, so I'm checking in this one. So if I plug in 4/3 for s, minus 3 times 5/3, does that equal 5? -5? It does not. And what does that mean? This system of equations has no solution. And which means there does not exist a t and an s where these two things, L1 and L2, will ever coincide, which means that they do not intersect one another. They're skew.
But if 2 out of the 3 were wrong, but 1 was right, that would still, what would we conclude?
If 2 out of the 3,
So like we wanted to make sure it doesn't intersect, if they're not parallel and they're not orthogonal. So if, let's say they were, like, would they always either be all there or none there?
all or none,
Yeah.
yes.
Okay.
Yeah, at least I believe that's the way this book is defining skew. I've seen skew worded different ways.
If they're parallel, they can't intersect unless they're, you know what I mean? So like.
Yeah, if they're parallel, right? If they're parallel, then they would not have to intersect, but they could, right?
Wait, so you're trying to find values where they're not parallel and they do not intersect. That kind of like
Or like
that
it can't be
contradicts each
parallel
other
and
because-
orthogonal at the same time.
Wait a minute,
Well,
hold
we
on.
already-
Hold on, one thing at a time.
because for them to not intersect, they have to be parallel.
For what, for two lines to not intersect?
They have to be parallel.
In two-dimensional space.
Oh my gosh!
It could be like that.
Yeah,
I forgot.
yeah. See, the 3D is what makes this worth doing. Because if you're in 2D, we can stick to pretty much everything we already know in Euclidean geometry and follow all the rules and stick with y equals mx plus b because it's a little easier to work with, right? But once you go to 3D, and actually this extends to 4D, 5D, 6D, the vector equation of a line does not change when you go into higher dimensions. If you want to know the vector equation of a line in four-dimensional space, it's going to be something like R naught plus TV, right? It's the same formula except that this vector is 4 components instead of 3. And that vector is 4 components instead of 3. And you go to 5-dimensional space, same thing. So very general, very general. In fact, this might actually be a little bit mind-blowing. Let's see if no, I'm not going to say this warrants mind-blowing. But in two-dimensional space, right? In two-dimensional space, right? This turns into, let's see, some two-dimensional vector, right? Let me just call it x. No, I'll just call it x. Yeah, I'll call it x and y. Shit. Okay. Plus t times v, and v is two-dimensional, right? I'll call it ab. Now, this is my vector right here, right? I just add these together. So I get x plus ta, and then y plus tb, right? Agreed? So when you look at this equation right here, right? Y equals mx plus b. If you were to write that as an ordered pair, when you graph it, it's x here, and then this is mx plus b, isn't it? Like your x coordinate is x, but your y coordinate is that. There's a way here that if we solve this for t, right? We solve this for t and plug in. If I solve that for t, see, I should have used x1, y1. I'm getting way past myself here. What I'm trying to get at is what are the symmetric equations for this look like? What does the symmetric equations look like for this? You eliminate t, don't you?
Yeah.
Because you solve for t and then you set them equal to each other. If you eliminate t and solve these and set these equal to each other, what are the only two real variables that you'll have? X and y, and then it basically becomes this. You've got this equation. In other words, since you only have two, the symmetric equations only include two things, it's basically this. It's basically this. You have the x and the y, and then you have the slope, which comes from these two letters, and then this right here would come from like these two. I leave it as an exercise for yourself to do it, but you could basically show that in two-dimensional space, why use that? Because it all just turns into this at the end. Okay. Can we move on? All right, let's continue. Are there any other questions on this? Because I stopped here. Yes.
So we would have, for doing the scalar multiple, the very first we did, we would have found out that they
Were parallel?
Then we could have stopped there.
Yeah, we could have stopped. But I don't think see, look, it says here, determine that these are skew. So that it should have just said show their skew. Because then that forces you to check all three. Yeah. Moving along. Okay, now we move on to planes. Now, I've always thought this is a little weird because when we do lines, we say, hey, look, we've dealt with lines in the past, y equals mx plus b, but now we're going to look at lines from a perspective of vectors, right? So I think it would be natural for you to now say, oh, you know, planes, we're going to start looking at these in the perspective of vectors. But that's actually not quite what happens. So before we even get into it, let's just make sure we all understand what you need to define a plane. So we know you need 2 points to define a line. What do you need to define a plane in three-dimensional space? 3 points, 3 distinct points, right? So as long as you have 3 points that are not all like laying on top of each other, then there is only one plane through those 3 points. So to do a line, we needed a line. We needed a point on the line and a direction vector, right? Or someone could give me 2 points and then I could create it myself. So that's what we needed for lines. But for planes, we need to have 3 points on a plane to be able to define it, right? Now, we can see below, to clearly define a plane, we need 3 points. Now, what we're going to do with those points, just follow me through here, is we are going to take any 2 points and create vectors. Now, keep in mind, those vectors go from the origin to those points, right? Now, I'm going to now look at the vectors that are going from this point to this point and this point to that point. You'll see it? What are those 2 red vectors live on that plane, don't they? Okay, so I'm going to take these others out of here. We really don't need those. But we have those 2 vectors can be created. Someone gives me 3 points, I can create those vectors. But now I'm going to take their cross product. Cross product. And remember, the big result from last class is that if you take 2 vectors and cross product them, you get a vector that's orthogonal to both, right? So if I cross product those vectors, I get that vector which is orthogonal to my plane, right? It's orthogonal to my plane. Now, why is that important? Well, let me try and illustrate this. We just said that in order to define a plane, you need 3 points, right? So 1, 2, 3 points, that would define this plane. But I think you can actually do it with less information. What if I give you just one point and that vector? Would that be enough? So what if I give you one point in space, and I tell you that this vector is orthogonal to the plane? Then there is only one plane that can do that, right? There's only this plane right here. Can't tilt it at all, this direction, right? Can't tilt it this direction. I mean, there's, as soon as you tilt it a little bit different, then this is no longer orthogonal to the plane, right? So 3 points would work. Yes, I agree. 3 points will define a plane. But if you just give me 1 point and this very special vector that is orthogonal to the plane, that will be enough also. Do y'all agree with that? You look skeptical. This vector has an important name. It's called the normal vector of the plane. The normal vector. So that's what I say here, the normal vector of the plane. So it turns out that in order to define a plane, all we need is a point on the plane and any normal vector to the plane. That means any vector that's perpendicular to the plane. Now, if somebody gives us a point, we'll call it x naught, y naught, z naught, and they give us a normal vector, which we're going to use n for normal, and we say that vector is the vector ABC. If that is any normal vector to the plane, then this is the equation of the plane, right there. So I'm going to write that down on the side here, or maybe I'll write it up here. A x minus x naught plus b y minus y naught plus c z minus z naught equals 0. And notice in that equation of that plane, there are no vectors, okay? There are no vectors in that equation of that plane. And look, just think about this, college algebra. That right there, hopefully in college algebra they told you that when you have a linear equation with 3 variables that this defines a plane. No? Did they tell you that?
They didn't.
They didn't? So you know when you're solving a system of equations and you have 3 of these? You have 3 equations, 3 unknowns? You're trying to figure out where 3 planes hit each other in 3-dimensional space. You're trying to find their intersection. That's what you're doing. But just FYI, this is 3 variables all raised to the first power in an equation like that. That is a plane. This is how you get the equation of it. This right here would generate something like that. But there's something really important about this. If you look at this equation, these coefficients, a, b, and c, are always going to be the direction vector. I mean, sorry, not direction vector, the normal vector, the components of the normal vector. And then your x naught, y naught, z naught is just a point, any point on the plane. Super powerful formula. Let's use it. Find the equation of the plane through these 3 points. Okay. Adam. I'm going to draw the 3 points for you, Adam. We're in 3-dimensional space. There they are. I've given you those 3 points, and I want the equation of the plane. So, Adam, my question to you is, what 2 pieces of information do you need to define a plane?
We have the points. We only need 1 point. Right?
We need 1 point, okay? So we need a point and the normal vector. That's it. From here on out, when you're thinking in this class about planes, say to yourself, all I need to define a plane is 1 point and a vector that is normal to the plane, right? So here we have a point, right? Check, we've got that. So why don't we call this one right here 1, 2, 14. Why don't we call that point x naught, y naught, z naught. Notice this is a point, not a vector. That's the point 1, 2, 14. So all that's left now, Adam, right, is to find this vector. Question, right? That's what we need. And how are we going to get that vector, Fernando?